Hello, this is the second video in a series about cosmology that presents a new idea called black marble theory. And I'm going to introduce two original ideas called black marbles and bright energy. Both of these ideas are simple and easy to understand, and they don't need anything more than ordinary and familiar physics to explain them. But when you add them to the current theories, they provide logical and plausible answers to the great mysteries in cosmology today. In this video, I'll introduce the idea of black matter. And the premise is this: there's a state of matter called black matter that hadn't been discovered up to now, but when it's taken into account with all else we know about the universe, it's going to fill in most of the areas we regard as mysteries today. I'll describe it in detail in a moment, but first, let's review what we already know about ordinary matter in the universe. The matter that we know today can exist in nature in one of 6 states. We recognize them as gas, liquid, solid, plasma, such as we see in the sun, degenerate matter, which we find in very small, dense stars called white dwarfs, and neutron matter, which exists in even smaller, denser objects called neutron stars. Now, most of the volume of matter in these states consists of space. The space is filled with energy and tiny subatomic particles of ordinary matter. But as we move from the gaseous state to the neutron matter, the amount of space gets less at every stage. And the reason, as we'll soon see, is that matter has the property of contracting the volume of space in its vicinity. If there's a lot of matter, such as we see in stars, it will contract the space into extremely small volumes unless some force prevents it. Well, in stars, that preventing force is the energy produced as the star uses its hydrogen fuel for nuclear reactions. When the fuel is used up, the gravity of matter will take over, and the remnants of the star will be compressed into a denser state. We'll describe this process in more detail in a moment, but here's the fundamental premise that we're getting to. At each stage, there is less space remaining in the matter. And I'm proposing that it will reach a final 7th stage where there's no space at all. And this is the state of matter that I call black matter. It still has finite volume, but there is no space remaining in it, which makes it the densest stuff that exists in the universe. It has all of the mass that comprises it compressed by its own gravity into a compact sphere. And I call this sphere a black marble. It's made of black matter, which is incompressible and inert. If the black marble is big enough, it will warp the space in its vicinity into an object that we call a black hole. So there's a black marble at the center of every black hole. Now, black matter lies at the heart of black marble theory, and it's the only addition I'm proposing to add to the current content of cosmological theory concerning matter. Everything else in black marble theory is based on common physical processes that we know and we can observe. The logical extension of this idea will challenge some physical processes that we can't observe and that we aren't too sure about, but we'll get to that later. But for now, if the idea of black matter seems plausible, I'd like to keep it in mind as we go forward and see what the universe will look like when we integrate black marble theory into cosmological science. So, let's begin in this video to describe the universe we live in and how it came to be the way it is. And in later parts, we'll take up the questions that still face us and see how black marble theory provides plausible answers. We'll start by describing what the universe is made of. and it has three components: matter, energy, and space. Now, we have pretty strong intuitive notions about the nature of each one of them, but it turns out that none of them is exactly what it seems to be. For example, matter and energy interact with each other according to the laws of Galileo and Newton at ordinary speeds, but their behavior changes radically when velocity approaches the speed of light. And perhaps the least understood component is space. They say if you want to know what water is like, don't ask a fish. Well, likewise, we creatures that live in space tend to think of it as a big three-dimensional volume that we move around in, and it's obvious and it deserves no further thought. Well, nothing could be further from the truth. Albert Einstein showed us in his general theory of relativity that space is malleable and is contracted when it's in the vicinity of matter. He showed that this curvature, among other things, results in producing the effect we call gravity. And we live in this curved space. In the room you're in, the space is more compacted down by your feet than it is up by your head. You know this because you remain firmly planted on the floor. Now, energy, on the other hand, when released into space, will expand it. And when we think about the universe, we need to keep these two factors in mind. Matter contracts space, and energy expands it. Now, at the present time, the tug of war between these two effects is being won by energy, and the space in the universe is expanding. Current cosmology theory has developed formulas that define how the rate of expansion is determined by the components that affect it, and we'll come back to this subject later when we discuss dark matter and energy. But for now, let's just accept that it's the interaction of matter and energy that accounts for the structure of the universe, and take a closer look at them. We're pretty familiar with ordinary matter. It's the stuff we're made of, and everything we see is made of it. And for most of our existence, we thought it was all there was. It's made of atoms, and we normally see it in three states. It can float around as a gas, or slosh around as a liquid, or the atoms can form rigid structure that we call solid matter. Well, I put quotations around the word solid because we've learned that atoms are small components of matter that are constructed with electron particles surrounding a tiny nucleus, but they're mostly empty space. The reason I can't punch my fist through a solid table is that the electrons surrounding the atoms are negatively charged and they repel each other through electromagnetic force. But nevertheless, the atoms themselves are mostly empty space. Now, there's a fourth common state that occurs when the temperature of the matter gets very high, as it does in stars like our sun. It's called plasma, and in this state, the atoms break down into an energetic soup. And, because most of the ordinary matter we can see is in stars, plasma is the most common state of ordinary matter in the universe. Now, the plasma in stars is heated by nuclear reactions that convert the matter in their cores to energy. This energy expands space, and it tries to blow the star apart. But this is prevented by the gravity of the matter in the star. So as long as the nuclear reactions keep going, the star is stable. The energy and the gravity are in equilibrium. But when it runs out of the matter it uses for fuel, the energy that supported the star is no longer there. And gravity will take over and begin to collapse the star into its final state. Now, what remains after the collapse will depend on how big the star was to begin with. As the mass increases, the space will be contracted out of it, and it will be crushed by gravity into smaller objects. If it's less than 8/10 of a solar mass, it will remain as ordinary matter. In a red dwarf star, these stars burn their fuel so slowly that they haven't had time since the universe began to burn out. Now, if the star is between 8/10 and 1.4 solar masses, it'll first swell up to form a red giant star, about 100 million miles in diameter, and then collapse into the small, dense object that we call a white dwarf. They're made of degenerate matter, where all of the space between the atoms is contracted out, and only the electron pressure prevents them from further collapse. Now, this is what will happen to our sun in about 5 billion years. Now, if they exceed 1.4 solar masses, the gravity will be so strong that it overcomes the electron pressure, and it contracts most of the remaining space out of the objects. The atomic electrons and protons are crushed into neutrons. The result is one of the most exotic bodies in the sky. It's about 12.5 miles in diameter, and it's so dense that a lump the size of a sugar cube would weigh about 100 million tons. And as these objects contract, their spin rate can increase like an ice skater's spin when she pulls in her arms, and the spin rate can increase up to hundreds of times per second. And these spinning neutron stars are called pulsars. But now suppose that the original matter was larger than about 2.5 solar masses. By now, as contraction continues, the gravity overcomes even the ability of the fundamental particles in the neutrons to resist. The remaining matter in the star will be compressed into perhaps the most exotic body in our universe, a black hole. Here's a short list of what we know about black holes. They're formed when stars collapse that have more than about 2.5 solar masses of matter, and the gravity is so strong that nothing can prevent the total collapse of the space in the original ordinary matter that made up the star. As the size decreases, the escape velocity increases. That's the minimum velocity that a particle would have to achieve to escape from the gravitational pull of the body. Now, when that escape velocity reaches the speed of light, nothing will ever be able to escape, even light itself. And when that happens, we formed a black hole. So, what happens to the matter left of the black hole? Well, current theories propose that it's compressed into an infinitesimal point that retains all of the gravity but has no dimension. And some physicists suggest that the matter disappears into another universe or pops up somewhere else in our universe through a white hole. They propose that at the center of every black hole, there's an object that exists in a single point with extreme gravity that they call a singularity. But I'm going to propose a theory that says singularities don't exist at all. And this is black marble theory. Now, so far in this video, what we've discussed can be found in any basic textbooks about cosmology. But now I'm going to propose a new premise to add to these books. I'm going to propose that in addition to the 6 states of matter that we've just discussed, matter can exist in a form we've never seen that I call black matter. So let's look at it more closely. Black matter is formed when ordinary matter is subjected to extreme gravity. Now, this gravity will contract the space that makes up most of the volume of ordinary matter until there's none left. And the residue that's left is black matter. It's been compressed as far as it can be, and the matter has changed its state into a substance with the highest density that can be reached in the universe. Now let me emphasize that point. Black matter is the most dense substance that can exist in the universe. It's matter that contains no space at all. Now, just like the ordinary matter will coalesce into a sphere if there's enough of it, the black matter will form a sphere that I call a black marble. So, at the center of every black hole, there's not a singularity. There's a black marble that contains no space, but it has a finite diameter and it has the maximum density that it's possible to exist. Black matter bears no resemblance at all to ordinary matter. Ordinary matter is made of discrete particles. There are just 12 kinds of fundamental ordinary particles in three groups called quarks, leptons, and bosons. And they can be put together in various combinations to produce all of the atomic particles to create atoms of ordinary matter. We'll review how this is done in more detail later, but for now, let's just keep in mind that ordinary matter particles are discrete objects. They're made of space, energy, and a little matter. And they're indivisible. You can't have half a quark. In a rough analogy, it would be like trying to cut a balloon in half. So imagine you have a tub full of balloons. You'll have a discrete number of them because you can't have a fractional balloon. Well, now imagine that you crushed the tub. You'd remove all of the air and the energy that kept them blown up, and you'd be left with a small ball of pure rubber. And the rubber ball could be cut up as fine as your knife will let you. Likewise, black matter, unlike ordinary matter, particles can be divided into any fractional size that you like. A scientist would say it's scale invariant. The balloon analogy leaves out a lot, but it provides a picture of a dense substance with no particle structure at all. Now, black matter lies at the heart of black marble theory. If this substance is formed as I've described and exists as a new state of matter that we haven't been able to observe, it will explain many questions about the universe. In particular, I'm going to propose that the Big Bang itself resulted from the explosion of a very large black marble 14 billion years ago that created the universe we live in. And we'll begin this journey in the next video in this series.